Hello and welcome back to Engineers Olympiad, where learning meets success. We're discussing the fundamentals and basic concepts of bridge engineering. We have discussed what is a bridge and various forms of bridge. 3 video lectures are already up on the channel. You can watch those videos in case you missed them before watching this video. But before starting this video, let's quickly recapitulate what we discussed in the previous video lecture. Suspension bridge. We discussed that a suspension bridge is that type of bridge in which a bridge deck is hung below suspension cables by means of vertical hangers or suspenders. By means of vertical hangers or suspenders, that means the bridge deck is essentially hung below the suspension cables by vertical hangers or suspenders in case of a suspension bridge. That means we use hangers. That's why they're known as hangers, because they hung the deck of the bridge below the suspension cable, or suspenders because they suspend the deck. That's why it's known as a suspension bridge. All right, and these network of cables essentially eliminate the need of intermediate piers, and that's why suspension bridges are the solution for creating longest spans without need for intermediate supports or piers. Spans in excess of 900 meters can only be created using or employing a suspension bridge. All right, we discussed each and everything in detail in the previous video lecture. You can watch that video before watching this video. And in this video, we are going to discuss the 6th basic form of a bridge, that is a cable stayed bridge. We learned that there are 7 basic forms of bridges. The first one is beam bridge or a girder bridge. The second one is a truss bridge. Then we discuss arch, then cantilever, then suspension. Now we are going to discuss cable stayed bridge. What is a cable stayed bridge? A cable stayed bridge is a bridge whose deck is also suspended by multiple cables that run down to the main girder from one or more than one towers. All right, so a cable stayed bridge is a bridge whose deck is suspended by multiple cables that run down to the main girder of the bridge deck from one or more than one towers. All right, so a cable stayed bridge is that type of bridge whose deck is also suspended by means of multiple cables that run down to the main girder of the deck of the cable stayed bridge from one or more than one towers. This type of bridge was developed in Germany, cable stayed bridge. It was developed in Germany, and the essential components of a cable stayed bridge are the first one is the inclined cables which suspend the bridge deck, inclined cables. Then we have towers, which are also known as pylons. And then we have the bridge deck. All right, so a bridge whose deck remains suspended by virtue of multiple cable system that runs down to the main girder of the bridge deck from one or more than one towers is known as a cable stayed bridge, and this was developed in Germany. This is a picture of a cable stayed bridge. These are the towers. They are embedded in the foundation, and this These you can see here, these are the inclined cables, and these inclined cables hung the bridge deck. That means the bridge deck in case of a cable stayed bridge is also suspended by means of these multiple cables, which are known as inclined cables. These are the towers which remain embedded in the foundation and also are known as the pylons, and this is essentially a bridge deck. All right, let me rub it first. So we have learned that in a cable stayed bridge, the bridge deck remains hung or suspended by means of a inclined cable and tower system. All right. Now in a cable stayed bridge, the vertical loads are carried by these nearly straight. Their function is to carry the loads of the deck. So the loads of the deck, vertical loads, they are carried by these nearly straight inclined cables. They are straight but they remain inclined cables which are in tension. They remain in tension. And then the load is transferred from these cables to the towers, and then from towers to the foundations below. All right. So the load transfer mechanism of a cable stayed bridge is that the vertical loads from the deck are carried by nearly straight inclined cables which are in tension. Then from the cables, the load gets transferred to the towers, and ultimately from towers to the foundations below, because towers are embedded in foundations. All right. So these towers transfer the cable forces to the foundation through vertical compression. We have studied that these cables remain in tension, and the tensile forces in the stay cables induce horizontal compression in the deck. Let me rub it first and I'll explain it to you. The loads from the deck in case of a cable stayed bridge are carried by nearly straight inclined cables which remain in tension, and the tensile forces in the stay cables induce horizontal compression in the deck. Horizontal compression in the bridge deck in case of cable stayed bridge. All right. So the vertical loads that come on the bridge deck in case of a cable stayed bridge are transferred first to these inclined cables which are nearly straight but remain inclined. They are always in tension. Then they transfer these loads to these towers, and these towers carry the loads, or rather transfer the loads to the foundation by vertical compression, and the tensile forces in these inclined cables induce horizontal compression in the bridge deck in case of a cable stayed bridge. All right. Now, what is the role of this cable and tower system? In simple forms, we may say that the cables provided above the deck and connected to the towers, they permit elimination of intermediate pairs thus facilitating a larger width for the purpose of navigation. For the purpose of navigation. All right. When we have hung the bridge deck by means of these inclined cables and tower system, we eliminate the need for intermediate piers because the deck of the bridge remains suspended by this cable and tower system, so we don't have a need to go for intermediate supports, or we can create a long span without the intermediate piers or supports in between. Thus we are facilitating a larger width below the bridge deck so that our navigation requirements are not hampered, the passing of ships is not obstructed, or for that matter any other river traffic. All right, so this is the essential function of a cable tower system, that the need for intermediate piers is eliminated. We can go on creating longer spans, thus we are facilitating a larger width for the purpose of navigation. All right, the cable stayed bridge is also similar to suspension bridge, except the fact that there are no suspenders in the cable stayed bridge. The suspenders in case of a suspension bridge, which essentially hung the bridge deck below the suspension cables, and they transfer the loads of the bridge deck in case of a suspension bridge to the suspension cable or the main cable. But the suspenders in case of a cable stayed bridge, you can see there are no suspenders. All right, there are no suspenders in case of a cable stayed bridge, unlike suspension bridges. All right, because in a cable stayed bridge the cables are directly stretched from towers and connected to the decking. The cables remain, I will write it down for you. The cables are directly stretched from towers and are connected with the bridge decking. You can see here in the picture that these inclined cables, they are directly stretched from the towers and connected with the main girder or the bridge decking system. Hence there are no suspenders as in the case of a suspension bridge in a cable stayed bridge. That means we have one more advantage, that there are no special external anchorages required. I'll show you the diagram of a suspension bridge, wherein we have hangers or suspenders, and then we have main cables, suspension cables, and then we need anchorages for these suspension cables on either sides, which are massive concrete blocks as already discussed. But in case of a cable stayed bridge, there are no hangers. Cables remain directly suspended from tower on the one end. They are connected to the tower of the cable stayed bridge on one end, and they are also connected to the bridge girder on the another end. That means no suspenders are there. Also, we don't require any external anchorages, because the anchorage at one end is done with the tower and anchorage at the other end is done with the girder. So these cables remain connected with the or anchored between the tower and the girder of the bridge deck system in case of cable stayed bridge, and no suspenders are present in a cable stayed bridge unlike suspension bridge. Also, we don't need any external anchorages in a cable stayed bridge unlike suspension bridges. The cables remain connected or anchored at one end to the tower and on the other end to the girder. All right, the early cable stayed bridges, they used or were mainly constructed using steel for stay cables. We use steel for these stay cables and deck and towers as well. So in earlier times, the cable stayed bridges were mainly constructed using steel for both stay cables, deck as well as the towers. But in some of the recent constructions nowadays, the deck and the towers have been constructed in structural concrete or a combination of steel and concrete. In recent constructions that have been carried out across the world, they have used structural concrete, or a combination of steel and concrete, or a combination of steel and concrete, for stay cables, deck, as well as the towers in case of a cable stay bridge. Right. Now we have two configurations. The deck in case of a stay cable or a cable stayed bridge is supported by a number of cables. We have two configurations. Let me show you the picture. This and this. The first configuration is that the deck in case of a cable stayed bridge is supported either by a number of cables which are meeting in a bunch at the tower. These are the inclined cables. They are meeting in a bunch at the tower, and this type is known as fan form. This is a fan-shaped multi-stay cable system wherein the cables that support the bridge deck in case of a cable stayed bridge, they meet in a bunch at the tower. And then we have another form. This is known as harp-shaped multi-stay cable system, wherein these inclined cables join at different levels on the tower. They are not meeting in a bunch, they are joined at different levels in the tower, hence harp shape. I'll write it down. We have two configurations, fan shaped and harp shaped. This is where the cables, inclined cables or the stay cables, meet in a bunch at the tower. That is a fan-shaped multi-stay cable system. Or if these cables meet at different levels at the tower and not in a bunch, that gives rise to harp-shaped multi-stay cable system. So this is a fan-shaped multi-stay cable system wherein inclined cables meet in a bunch at the tower, and this is a harp-shaped multi-stay cable system wherein these stay cables or inclined cables meet at different levels on the towers or pylons. All right, moving on. Let me rub it first. Now these stay cables, they constitute a critical component of a cable stayed bridge, as they carry the load of the deck and transfer it to the tower. We have learned that they always remain in the tension, and the tensile forces are then transferred to the tower, which transfers it to the foundation blow through vertical compression, and the tensile forces in the stay cables induce horizontal compression in the deck. All right, now these stay cables constitute a critical component in case of a cable stayed bridge because they essentially carry the load of the bridge deck and transfer it to the pylons, then transfer it to the towers or the pylons. That means we should select, the need arises that we have to select these stay cables with utmost care. All right, because they essentially form the most important component in case of a cable stay bridge. The bridge deck remains suspended by means of these nearly straight inclined cables. Hence, they are one of the most important and critical component of a cable stayed bridge. We should select these cables with utmost care, and we should make sure that most of the requirements, as I'll list down, are met when we are going to select these stay cables. The first one is that they should have high load carrying capacity. All right, so these are the main requirements of a cable stayed bridge cables. That first one is that they should have a high load carrying capacity. Second one, they should have a high and stable Young's modulus of elasticity. High and stable Young's modulus of elasticity. Compact cross section is the another requirement of these stay cables. They should have compact cross section. High fatigue resistance. High fatigue resistance. They should also possess ease in corrosion protection. There should be handling convenience as well. And most important of all, low cost, because economics is one of the most important parameters in engineering. All right, so these are the requirements of stay cables. Since they are the essential component of a cable stayed bridge, they must have high load carrying capacity, high and stable Young's modulus of elasticity, compact cross section, high fatigue resistance, ease in corrosion protection, handling convenience, and low cost. All right. Since in recent times we have replaced steel by structural concrete or a combination of structural concrete and steel, but in earlier times we used to construct these cable stayed bridges, all of the three components rather, deck, tower and the cables, by steel. All right. The UTS, the ultimate tensile strength. Ultimate tensile strength of the wire which forms these stay cables is of the order of, or should be of the order of, 1600 MPa. MPa, Newton per mm square. All right. So the ultimate tensile strength of the wire of which constitutes these stay cables should be of the order of 1600 MPa or 1600 Newton per mm square. Now comes another challenge. We cannot leave these stay cables exposed. We have to provide necessary sheathing, and sheathing in case of stay cables is done by using black polyethylene tubes. All right. So it's quite necessary that we exercise extreme care for the protection of the cables. From corrosion, of course. And for that purpose, we place the cables in tubes which are made of black polyethylene, and those tubes are also tightly connected with the anchorages. The anchorage at the one end is done with the tower, and at the other end is done with the main girder or the bridge deck itself. So for the purpose of protection of these cables from corrosion, we go for sheathing, and sheathing is done by means of black polyethylene tubes. We place these cables, these stay cables, in tubes which also remain tightly connected to the anchorages. That means on one end to the tower and on the other end to the bridge deck. And these tubes, as already discussed, they are made of black polyethylene. That gives them essential protection from the corrosion, and this forms a cable sheath. And I'll show you one diagram of this cable sheath over here. This is a typical section of a stay cable, or you may say cable sheath, wherein this is the polyethylene pipe or tube and then we place these wire strands or our cables inside, and then this is the cement grout. What is its function? I'll tell you. And this is the helical spacer strand. So this forms your cable sheath. When sheathing is done by placing these cables inside black polyethylene tubes so that they are prevented from harsh environmental conditions which will cause corrosion and other problems. The voids around the wires, when we place them in this sheathing, they are then filled with some anti-corrosive material that is, mostly we use cement grout. All right. When we place these cables inside the black polyethylene tubes, then we go on filling the voids, if any, between these cables by means of a cement grout, which is essentially a anti-corrosive material. All right. So you can once again see the typical section of a stay cable. This is the polyethylene tube or pipe. These are your wire strands or parallel wires. This is the helical spacer strand, and the voids are filled by means of injection of suitable anti-corrosive material, particularly cement grout. All right. We fill it by injection. We inject cement grout so that we can fill all the voids. This was about the protection of the cables from corrosion and the sheathing to be done. There comes one more challenge, and that is of the sag of the cable under its own weight. The cable may sag because of its dead load or under its own weight, and this introduces a new complication or a challenge in case of a cable stayed bridges, but for that solution is pre-stressing. All right, since the design of these cables must be done with utmost care, because the sag of the cable under its own weight introduces a complication and a challenge. For that purpose, the cables are pre-stressed by introducing additional tensile forces in the cable. We introduce additional tensile forces in the cable. That means we pre-stress our cables, and that has many advantages. Let me write them one by one. Because the sag of the cable under its own weight is a big challenge and a problem, we counter that by pre-stressing the cables by introducing additional tensile forces in the cable. Now it has three important functions. First one is it improves the stress in the main girder and tower at the completion stage. It improves the stress in the main girder and the tower at completion stage. The second advantage of going for pre-stressing is that it prevents lowering of rigidity due to sagging of cable. And the third one is it optimizes the cable condition for the erection. All right. Since we learned that the stress in the cable is improved, or we go on inducing additional stresses by means of pre-stressing these cables, we go on introducing additional tensile forces in the cables, and that gives us three most advantages. The first one is that it improves the stress in the main girder and the tower at the completion stage. It prevents the lowering of rigidity due to sagging of the cables, because the sag of the cables under its own weight is also a big challenge in case of a cable stayed bridge. And the third one is that it optimizes the cable condition for the erection. All right, so this was about the pre-stressing. And this is essentially a difference between suspension bridge and the cable stayed bridge, because in suspension bridges, our cables are not pre-stressed. All right. Either our main cable or suspension cable, or for that matter, our hangers or suspenders, they're not pre-stressed. They're not pre-stressed in case of a suspension bridges. But in case of a cable stayed bridges, cables are pre-stressed for various purposes that we have learned. All right. Currently, the steel that we use for the cables have a UTS of, as already discussed, 1600 MPa. But nowadays, we are also exploring carbon fiber cables having UTS of about 3300 MPa. They're also under development. And these are said to have negligible corrosion, and they also possess high fatigue resistance. Carbon fiber cables. They're also under development, and they have a UTS, or the ultimate tensile strength, of 3300 MPa, 3300 Newton per mm square. But the challenge is that they are quite expensive. Hence, they will badly impact our economics. Quite expensive. All right, so this was about the cable stayed bridge. Let us quickly recapitulate. A cable stayed bridge is a bridge in which the bridge deck remains suspended by means of the cables which are connected to the towers. Towers are embedded in the foundation. The vertical loads from the bridge deck are first transferred to these nearly straight inclined cables, or the stay cables, which remain in tension. Then they transfer the loads to the towers, and the towers, by means of vertical compression, transfer these forces to the foundations below, because the towers or the pylons are also embedded in the foundation. If the cables meet, and the role and the very important advantage of going for this system is, the cable and tower system, is that we can eliminate the need for the intermediate pairs, hence providing a larger width for the purposes of navigation, etc. And we can create longer spans by this assembly. And we have also learned that if the cables meet in a bunch at the tower, then that multi-stay cable system is known as a fan shaped, or if they meet at multiple levels on the towers, then that is known as the harp shaped multi-cable stay system. And then we also discuss about the two challenges that we usually face. The first one is that we have to go for sheathing. We have to prevent or protect our cables from corrosion, and for that matter we place them inside black polyethylene tubes, which are also tightly connected to the anchorage, on the one end to the tower and on the other end to the girder in the ridge deck system. And the other challenge was the sag of the cable under its own weight. For that we go for pre-stressing, and pre-stressing, besides preventing the lowering of rigidity because of the sag of the cable also gives us two more advantages, which we also learned. And we also learned that the tensile strength of these cables is of the order of 1600 MPa, but nowadays carbon fiber cables which have the UTS of 3300 MPa is also under development, which is said to possess negligible corrosion and high fatigue resistance, but are expensive. And the main requirements of a stay cable, because they form the essential component of a cable stayed bridge system, they must have certain requirements, which we also discussed. Now we are going to discuss the advantages and the disadvantages of these bridges. First, we'll study about the advantages. The first one is efficient use of materials. I'll write it down for you. Efficient use of materials. Cable stayed bridges use less material than suspension bridges. So these cable stayed bridges use less material than suspension bridges, thus making them cost effective while still being structurally sound. So they are cost effective. Then suspension bridges and also structurally sound. I will also write it down for you. So the first advantage of these cable stayed bridges is that efficient use of materials is being done in case of cable stayed bridges. They use less material than the suspension bridges, hence making them quite cost effective while still they are being structurally sound. This is the first advantage, efficient use of materials. Second one, faster construction. Faster construction. These bridges can generally be built faster than suspension bridges because they don't require the extensive cable and tower systems. Extensive cable, tower and anchorage system is not required in case of a cable stayed bridge, unlike suspension bridge. That's why they can be constructed relatively faster than the suspension bridges, which is their another advantage, faster construction. All right, let's study the third one, lower maintenance costs. Lower maintenance costs. Compared to suspension bridges, which every now and then require painting and all, they require less maintenance because they have fewer parts which are exposed to wear and tear. They are not exposed to wear and tear, only a few remain exposed to wear and tear, hence, particularly in terms of cables and anchorages, you must know that. So they don't require much of the maintenance, unlike suspension bridges, wherein every now and then we have to go for painting and all, because in case of a cable stayed bridge, very few parts remain exposed to wear and tear, especially in terms of cables and anchorages. So maintenance costs are reduced, and this is because of the sheathing that we do in case of cable stayed bridges. Fourth one, aesthetic appeal. Aesthetic appeal. These cable stayed bridges, they often present a modern, sleek look. Which makes them quite attractive for cityscapes and the scenic areas. All right, these cable-stayed bridges, they present quite modern and sleek look. That's why they become quite attractive for cityscapes and scenic areas. Fifth advantage is that they have efficient load distribution. Efficient load distribution. These cables distribute the load efficiently, thus reducing the stress on the supporting towers, thus enabling the bridge to handle the traffic well. So the cables, in case of a stay cable, they efficiently distribute the loads. That's why they reduce the stress on the supporting towers. Thus, they make the bridge efficient enough to handle the traffic quite well. This is the fifth advantage of these cable-stayed bridges. Next one, medium to long span capability. Medium to long span capability. These are ideal for the spans ranging from 200 meters to 900 meters. Cable-stayed bridges are ideal for spans ranging from 200 meters to 900 meters. Beyond 900 meters, we have to essentially go for a suspension bridge. All right. This covers many bridge design needs, thus making them quite versatile. They're quite versatile because they can be constructed for the spans ranging from 200 meters to 900 meters, which covers many bridge design needs, thus making them quite versatile. This was the sixth advantage that we are studying here. The last advantage that we are studying here about the cable-stayed bridges is that less foundation depth. We have learned in suspension bridge there was a disadvantage that in case we didn't had favorable conditions, we have to go for extensive foundations for a cable for a suspension bridge. But here this is not a limitation. Compared to suspension bridges, cable-stayed bridges typically require less deep foundations, making them quite versatile for the areas with less favorable soil conditions. All right. So in areas where there are not quite good soil conditions or favorable, they don't require extensive foundation systems. Unlike suspension bridge, they require comparatively less deep foundations. In those areas also where we don't have good favorable soil conditions, that is one of their major advantage, that compared to suspension bridges, cable-stayed bridges typically require less deep foundations. Thus, they are suitable for areas with less favorable soil conditions. This was about the advantages. Now let's study about disadvantages. The first one is limited suitability for very long spans. Limited suitability for very long spans because they're only ideal for span ranging from 200 meters to 900 meters. Beyond 900 meters, we have to go for essentially suspension bridge. All right, so they have limited suitability for long spans, for very long spans. Next, complex design. The designing is rather complex. This is one of the drawback of these cable-stayed bridges. The next one is wind and seismic forces, or seismic sensitivity rather. Like all other tall structures, these cable-stayed bridges also can be sensitive to wind and seismic forces. All right. Fourth disadvantage is initial construction cost. While they are cheaper to maintain, the initial construction cost can still be quite high. we have learned that they are quite easy to maintain, and maintenance is very less, unlike that of a suspension bridge, which every now and then requires painting and all. Though maintenance costs are less, but the initial construction cost in case of cable stayed bridge can still be high because of the specialized materials and engineering needed, especially for very long spans beyond 500 meters. So this adds to the drawback of these cable stayed bridges, that they have high initial construction costs. Now, since we have praised their less maintenance costs, but some difficult conditions still possess many difficult challenges. The sixth disadvantage is maintenance of cables, because over time these cables can experience wear and corrosion, especially in those environments which are quite harsh. That means we have to go for regular inspections and replacements of cables as well. That is a big drawback in case of a cable stayed bridges, that if we are going to construct these cable stayed bridges in those environments which are quite harsh, then there the cables can experience wear and corrosion. Thus we have to go for regular inspections and replacements. That is quite tedious, and that adds to the drawback of these cable stayed bridges. So this was about the sixth basic form of bridges, the cable stayed bridges, which we discussed in this video lecture. Now we have the last one to discuss, that is the tied arch bridge or a bowstring bridge, that we'll discuss in the next or the upcoming video lecture, God willing. This was for today. Thank you for watching this video.